Good morning all. In this video we will discuss Kirchhoff's laws. In that we have Kirchhoff's current law and then Kirchhoff's voltage law. So we'll discuss one by one now. So in the previous class we discussed Ohm's law and its limitation. To overcome that limitations we have Kirchhoff's laws like KCL and then KVL. So already we discussed, right, the statement of Ohm's law. Temperature remains constant and current flowing through the conductor directly proportional to voltage, inversely proportional to resistance of the conductor with the temperature remains constant considering two ends of the conductor. And also limitation of Ohm's law we discussed in the previous classes. It is not applicable to non-linear devices such as thermocouple, thermistor, other temperature varying devices. And also it is not applicable to arc lamp. And also it is not applicable to liquid conductor such as silicon carbide and then gallium arsenide. It looks like a liquid but it will conduct, but temperature remains constant, but there is a no temperature remains constant, right? So similarly the last limitation like Ohm's law is not applicable to circuit having more number of nodes, more number of branches. So if it is complication will be there, means definitely the Ohm's law is not applicable. To overcome that problem we have this Kirchhoff's laws. Kirchhoff's current law, algebraic sum of the current meeting at a junction is equal to 0. So Kirchhoff's current will be there. See here, as you can see the diagram, there is I1 and I2 is entering, I3, I4, I5 is leaving. So algebraic sum of the current meeting at a junction, this is a junction, okay, this is junction, so is equal to 0. Our incoming current entering into the junction is equal to outgoing current from the junction. I mean incoming current is equal to outgoing current. See here, I1 and I2 are entering and I3, I4, I5 are leaving from the junction. That is KCL. So the statement says algebraic sum of the current meeting at a junction is equal to 0. Our current entering our current flowing towards the junction is equal to current flowing away from the junction. So this is the statement of KCL. And next we have a KVL. So as you can see the diagram, here there is a voltages V1, V2 will be there and R1, R2 will be there. So V1, V2 are the voltage sources and R1, R2 are the resistance of the circuit. So algebraic sum of the voltages around the loop is equal to 0. This is a complete loop will be there, right? Like complete one circuit. So there is no splitting of this branches or whatever, because this is a complete one cycle or one complete loop will be there. So that is KVL. Algebraic sum of the voltages around the loop is equal to 0. So we can say the statement as even can define like this: algebraic sum of the voltage drop and algebraic sum of the EMFs is equal to 0. That is sum of algebraic sum of the voltages and sum of algebraic sum of the voltage drop is equal to 0, or the equation becomes sigma IR plus sigma EMF is equal to 0. Otherwise we can explain, or we can tell the statement like this: algebraic sum of the voltages around the loop is equal to 0. Because if you take voltage drop, V is equal to IR, right? So that is voltage drop. So we can take here also voltage. All the values are voltage only. So that's why we can say algebraic sum of the voltages around the loop is equal to 0. So finally the statement of KCL, algebraic sum of the current meeting at a junction, you have to mention junction, and is equal to 0, and this KVL, algebraic sum of the voltages around the loop is equal to 0. So we will discuss in detail KCL. See here, this is a junction and I1 is entering and I2 is also entering and I3, I4 are leaving from the junction. This is the circuit diagram or illustration of KCL. So at any node, this is a node, okay, this is a node. A node, what is the meaning of node? A node is point where two or more elements meet, or two or more currents meeting at a particular point, that is node. And the sum of the incoming current, I mean incoming current is here we can say I1 is entering, okay, and I2 is also entering, I1 plus I2, and is equal to the sum of the outgoing current. So incoming current is equal to outgoing current. Outgoing currents are here I3 and I4. So equation becomes I1 plus I2 is equal to I3 plus I4. So we'll discuss KVL now in detail. So as you can see the diagram over here, there is a R1 and R2 connected in series, and then V1, V2 will be there. KVL, Kirchhoff's voltage law, the statement becomes algebraic sum of the voltage drop plus algebraic sum of the voltages. These two voltages, V1 and V2, and R1 and R2 is here present. So is equal to 0, or you can say the algebraic sum of the voltages around the loop is equal to 0. Just to write here, equation becomes V1 plus V2 is equal to IR1 plus IR2. So the current becomes I is equal to V1 plus V2 by R1 plus R2 according to Ohm's law. But here the loop will be there. Directly you can write I is equal to, if you want I current, okay, I current, I is equal to V1 plus V2 by R1 plus R2. Let's continue this topic, that is number of resistors are connected in series, that is R1, R2, R3, the resistances are in series connection, right? So as you can see the diagram, see here voltage drop across R1 is V1, R2 is V2, R3 is V3, and the total voltage is V, the current is flowing through the overall circuit is I. So in the figure shown like R1, R2, R3 as a symbol, right? So for the electrical standard, we are considering as a lamp. The lamp 1, lamp 2, lamp 3 will be there, and the battery will be there because this is a DC circuit topic. We can give AC supply also, but the topic itself DC circuits, right? The module name itself. So L1, L2, L3 are R1 plus R2 plus R3. The equivalent resistance by calculating total resistance, right? So if you want to calculate I, we can say total voltage divided by R1 plus R2 plus R3. So R equivalent is R1 plus R2 plus R3, right? And if you want to calculate power loss across resistance R1, so V1 square by R1, or V2 square by R2, or V3 square by R3, I can take I1 square R1, I1 square R2, I3 square R3. See, series circuit, definitely you can say the current always same. If it is parallel circuit, the current will be differ because same current will be flowing, right? Because there is a complete one loop will be there. So same current is flowing. This is series circuit. Next we have a resistance are connected in parallel. See, number of resistance R1, R2, R3 are connected in parallel. So the current will be differ. The voltage must be same. Keep it in your mind. And the physical example, I can take parallel circuit. The three number of lamps are connected in parallel. So if the one lamp is not working, the other two will be working, right? So the basic common sense, whatever the connection of home appliances or home power supply also, that is parallel connection. If suppose one home is disconnected from the power supply, that will not affect it to other two homes. Similarly, the one lamp is not working, definitely other two lamps will not be affected, right? So this is a power supply and this is a parallel circuit. The equivalent resistance becomes 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Next, resistance are connected in series parallel. As you can see the diagram over here, here the number of resistance, two resistances are connected in series and another two resistances are connected in parallel. This is the supply or the symbol. So symbolic representation, this one. There's just one circuit diagram consider. Finally, the current, voltage and power energy relations. So as you can see the diagram over here, there is a power, current, voltage, resistance in the inner circle, and if you want power, I square R, V square by R, and power is equal to VI, and I is equal to V by R, I is equal to P by V, and I is equal to root P by R. Similarly R and then similarly V. This is one complete analogy you can take. Next we have a power, energy, current and resistance, right? So power, electrical power is a rate at which electrical energy is transferred in the electrical circuit. Otherwise power is equal to work done by time, you can say, right? Energy by time. And current, flow of electrons, flow of charges, particular direction, particular time, particular conductor we have to mention. If you are answering as current is called as flow of charges, flow of electrons, that is 30 percentage completed. But if you want to complete 100 percentage definitions, so power or current or voltage, we have to mention particular conductor, particular direction, particular time, right? Current is equal to q by t, charge with respect to time or whatever. Voltage is potential difference between two ends of the conductor or two ends of this one wire or connections. Our electric potential is also defined as work done by unit charge, right? W by q, work done by unit charge. The SI unit is volts, and then joules per coulomb is this one unit. And resistance, opposition of flow of electrons are to resist the movement of electrons.